In electrical circuits, not all components respond instantly to changes in signals. Some components resist changes in voltage, while others resist changes in current. In this lesson, we will understand inductors, one of the two fundamental energy storage elements in circuit theory, and why their behavior is essential for both transient analysis and RF systems. An inductor is a passive electrical component that stores energy in the form of a magnetic field generated by electric current flowing through a coil of wire. When current passes through the conductor, it creates a magnetic flux around the coil, and this flux increases proportionally with current magnitude. The stored energy is not held in the wire itself, but in the surrounding electromagnetic field. In circuit theory, inductors are treated as ideal elements that relate voltage and current through a time-dependent relationship. Unlike resistors, which respond instantaneously, inductors introduce dynamic behavior because they oppose changes in current over time. This makes them essential for analyzing circuits where signals vary with time, especially in transient and AC conditions. The inductance value, measured in henries, determines how strongly the inductor resists changes in current. A higher inductance means a stronger induced voltage when current attempts to change, which directly affects circuit stability, filtering behavior, and energy transfer characteristics in both low-frequency and high-frequency systems. The operation of an inductor is governed by electromagnetic induction. When current flows through a coil, it generates a magnetic field, and this field stores energy proportional to the square of the current. If the current increases or decreases, the magnetic field must change accordingly, and this change induces a voltage that opposes the variation in current. This opposition is described by Lenz's law, which states that the induced voltage always acts in a direction that resists the change that created it. As a result, inductors naturally prevent abrupt changes in current. If the current tries to rise suddenly, the inductor generates a countervoltage that slows the increase. If the current tries to drop suddenly, it releases stored energy to maintain flow. At steady state in DC conditions, once the current becomes constant, the magnetic field stabilizes, and no further voltage is induced. In this condition, an ideal inductor behaves like a short circuit. However, during transitions or AC operation, its dynamic behavior becomes dominant and must be carefully considered in circuit analysis. An inductor can be understood as an electrical system with inertia. Just as physical objects resist changes in motion due to mass, inductors resist changes in current due to magnetic energy storage. This analogy helps bridge the gap between physical intuition and circuit behavior. A useful comparison is a heavy rotating flywheel in mechanical systems. When torque is applied, the flywheel does not instantly change speed, but gradually accelerates or decelerates due to stored kinetic energy. Similarly, an inductor does not allow current to change instantly, but smooths transitions by storing and releasing energy in its magnetic field. This property makes inductors extremely useful in systems where stability and smooth energy transfer are required. They reduce sudden fluctuations, filter unwanted variations, and control how energy moves through a circuit over time. In practical circuit design, inductors are essential in transient and AC analysis, especially in RL and RLC networks where time-dependent behavior defines system response. Engineers use inductors to control current dynamics, shape signal waveforms, and manage energy flow in both analog and power electronics systems. Inductors are widely used in power supplies to smooth current variations, in filters to separate frequency components, and in timing circuits where controlled delays are required. Their ability to store and release energy makes them key components in systems that must react predictably to changing electrical conditions. At higher frequencies, inductors become even more important because their impedance increases with frequency. This frequency-dependent behavior allows engineers to design circuits that selectively block or pass signals, which is fundamental in communication systems and signal processing networks. In RF engineering, inductors play a critical role in controlling frequency-selective behavior. Their impedance increases with frequency, which allows them to block high-frequency signals while allowing low-frequency signals to pass, making them essential in filtering and impedance matching networks. Inductors are also key components in resonant circuits, where they interact with capacitors to define natural oscillation frequencies. These LC resonance structures form the basis of oscillators, tuners, and frequency-selective filters used in communication systems. Understanding inductors is crucial for RF engineers because many high-frequency behaviors are dominated by inductive and capacitive effects rather than simple resistive behavior. This makes inductors a foundational element in both circuit theory and real-world RF system design. In this lesson, we learned that inductors store energy in a magnetic field and resist changes in current, creating time-dependent behavior that is fundamental to circuit theory. This property makes them essential for transient analysis, filtering, and frequency-dependent circuit design in both electronics and RF systems. In the next lesson, we will explore RC circuits and begin combining resistors with capacitors to analyze real-time dependent circuit behavior. If you found this useful, like the video, subscribe, and follow for the next lesson.